Hello, my name is Aaron Goldstein, student number G0001890. Demonstrating my project, a 4 to 20 milliamp calibrator, which I have dubbed analog calibrator. I work in the process control industry, and all of the analog signals that are interpreted by different flow computers or programmable logic controllers are, generally speaking, 4 to 20 milliamp signals. So what I've decided to build is a 4 to 20 milliamp simulator for use in my lab. I will be able to generate at least 4 of these into the packaging that I have currently purchased, but for the school project it will be a singular circuit. My circuit entails a differential op amp, a MOSFET, a variable resistor, 0 to 200 ohms. I'm using a 5.1 volt Zener diode for voltage regulation. Currently I have everything here set up. I'm powering my circuit. The power supply is a 12 volt power supply. I'm using a regulated DC power supply. As you can see, I get a voltage readout and a current draw off of it. Currently I'm drawing 56 mils. So it's a very low power circuit. I'm verifying my output of the circuit using my Fluke 789 process meter. My load I'm using a resistance decade box, which is currently set to 250 ohms. These are my taps for my current meter right now, my ammeter. I'm verifying the input power supply with my scope meter, checking for noise. As you can see, it's a very clean signal. And here we go. I'm going to, right now, at 4.5 milliamps. I also have a display that will be on the front panel showing percent of output. And as you can see, this is 3.1%, which matches the meter. So I'm going to vary the VR1. And as you can see, as I vary it, the meter is coming up, as is the display, matches. So let's dial it in there at 50%. There's 50% and is verified as well on my meter with right here 50%. And still no noise or anything else. I'm going to take the scope off of the power supply in. I'm going to put it on the output. And there you go, it is a clean output. So as you can see, there's no EMI interference on the circuit. Everything's pretty tolerable. And there you go. I will put this back here and I will drive the circuit to 100% to ensure that there's no saturation of the op amp. Okay, we're about at 100% even as verified on the display. And there we have it. The breadboard works. The physical prototype does work. As you can see, that it is a lot harder to breadboard, I have found out in real life, than it is on multisim. I had a couple go-rounds where apparently I didn't have something addressed correctly. I found it was easier to put the physical address of each connection on my print, and as you can see now, everything works as desired. This is my final circuit in its packaging and everything. I've transferred the circuit from the breadboard to a copper plated perf board and soldered all of the components on. Made some quick disconnect terminals for outside the board devices like my potentiometer, my current display, and the load terminals and the power supply terminals inside. Still using a regulated power supply and a Fluke 789 process meter for my load for a verification of the output of my device. Lessons learned, I did find that as everything that I tried for my resistors to get it calibrated, my voltage divider was not quite accurate enough to get it down exactly to 4 milliamps. I would have in the future, I would install trim pots on the important input to the differential op amp and the current resistors so that I could calibrate the voltages to the op amp. So all the way at the bottom I get 4.065, which is a 0.4% output. The same can be verified here. We'll go for a midpoint verification at 50%, which should be 12 milliamps. And it is 50%, 11.998 milliamps. And then all the way up, I get, I'm able to go over my 20 milliamps due to the bias of the resistor network, but I can achieve 20 milliamps, which is 100% output. And that's it.